couple minutes to go, and MES is on time, which is an achievement. So maybe I can warm up a little bit the ambience before MES starts. Maybe a little bit of history of MES, and also partially how OCP3 started. OCP3 or I was a young postdoc, original Norwegian, and then at the Danish Institute, and I became associate professor there. And I was teaching a class. I volunteered, so I highly recommend all the younger assistant professor or postdocs to volunteer to teach classes. So I volunteered to teach a class in Astronomy, and then a bunch of young kids took the course. I was lucky enough, they were all very smart. 3 of them, Thomas, Frandsen, and Bjarke Gudnason, were actually in that class. And they seemed to have liked it, and they asked for, can we do a master thesis with you? Okay. All 3 are and were extremely competitive within each other, with the others. It was really fun to have them around. And you know, we started playing around. All 3 were also relatively formal. MES went into the string theory. He did something which was very formal in his thesis. I think it's the only master's student of mine that came with a thesis of 200 pages, which we had to actually cut down to a few pages, fewer pages than that. Thomas was doing what was with symmetry, he was doing that stuff, and Bjarke was doing actually on phenomenology. All 3 of them are now professors. Some others also overhead. And Bjarke is professor now in Chinese Academy of Science. This high to the PhD in Italy. And they continued, thanks also to Thomas entered in the MBI PhD program. MES was enrolled there too, under Grant of Excellence I've got. And I was very lucky. Now, MES, since then, has drifted a little bit more toward phenomenology. He actually started loving it and doing that. They were really getting at each other a lot, and they still do. And that's great. I really enjoyed that. After that, after the PhD, MBI, MES moved to Oxford, where he did really great science there. He went in the news many times for his work with Subir about how you can, whether you can have effects of the dark matter of the sun, which is also hints on astrophysics I've been doing. So he's trained as a formal field theorist. I would still consider him a formal field theorist in many ways. I would say all my students are actually formal field theorists. But then that's actually the legs that gives you to then do basically anything you want. And he's been working for LHC phenomenology, astroparticle physics, and he's been extremely successful in all of these things. Now he's also building up a group of his own and stuff. He was also a Sapere Aude young investigator, and he was supposed to go also, was it Berkeley, right? So I was very lucky to be able to attract the students, and say all the other students I've got are also very good. But, you know, as David Gross says, your first students are always special to you in a way, because they're the ones that actually makes you, you know, change from being a postdoc to. And now, I also promised MES that this is going to be an interactive thing, since a good deal of the audience knows about this stuff, we're going to be tough. Right? That's, you will see also how a research environment works in our field. It's extremely competitive in every field, but it's really, and so we're going to have some fun about that. Hope you will enjoy. I don't know if MES wants to say two other things before it starts. Otherwise, I welcome Mess giving a talk about the naturalness of nature.
Yeah, thank you very much for the introduction. And it's 45 minutes roughly, right?
Yes.
Yeah, yeah. Okay, very good. So, yes, so I'll talk about the naturalness of nature. The point is, of course, that there could be a question mark here, but I haven't put it yet. So there are three reasons. So that this might seem tautology, but I'll make this more precise in such a way that it isn't anymore. And the point for choosing this topic for this type of seminar is several things. First of all, since this is a general institute, concepts of naturalness pervade many disciplines of science. So I'll briefly talk on that in the beginning. The other point is that the concept of naturalness, as used in particle physics, as we'll get to, actually provides us with the concept of naturalness, and the success in some sense of particle physics provides us today with a certain dilemma that I'll start out with, but it also provides us with a very practical tool actually to proceed in particle physics. So that's the third reason. So this is really today a tool, our concept of naturalness, in developing new theories and distinguishing good from bad theories in a sense. But of course it might be a wrong tool. So there will be a question mark to the end. Okay, but Francesco already introduced me, so I just gave a very short bio. As I said, I've been here since 2012, and before I was in Oxford, and I'm a PhD from the Danish Institute. And then I just wanted to, for those of you that are not aware of this, which I wasn't until recently, I'm now a member of the Young Academy, which is basically the kids club of the Royal Society, not the Royal Society, the Danish Society, what's the heck it's called? Danish Society of Sciences and Letters. Yeah. And so for the young scientists among you, I would say it's very relevant to consider entering into this. So this is basically an organization where we work on research politics from the point of view of young researchers, research outreach, and things like this. But especially the research politics, I think is very relevant for people interested in that to think about entering into this organization. So, okay, what I will talk about today, of course, deals with our natural history in the broadest sense. So trying to understand the evolution of the universe from the smallest scales at the earliest time that we can test and speculate about. So the Big Bang, or shortly after the Big Bang, and then after 14 billion years, to the largest scales that we observe in the universe today, such as galaxies, galaxy clusters, planets that allow the existence of us and allow the possibility that we can sit here today and ponder the evolution of ourselves, if you wish. Or you can do, if you don't like to ponder, you can do other things.
With the last picture, it could also be the end of time.
Yes, that's why I'm saying if you don't like to ponder, you can.
So maybe it's not evolution anymore.
You can do other things. Okay, so. And there's a very important. There's several important points to this diagram. First of all, this diagram shows you that the largest structures that we know of today, according to this standard cosmological model, are related to the smallest scales we can think about, because the universe itself was incredibly small shortly after its birth, if you wish. So the physics that has determined the large-scale structure of the universe today that allow our existence is determined by the smallest scales of matter that we can study. That also means that if we want to really understand the evolution of the universe, we need theories that can be extrapolated back to very early times, which, because the universe was also very small at that point, means very, very high energy. So we are today searching for theories that can be extrapolated as far back in energy as possible. And then, of course, we hit a very practical problem, namely, how do we then experimentally test those theories? Because, of course, higher energies also mean smaller scales, and the smaller scale, as you want to probe smaller and smaller scales, it gets experimentally harder and harder and harder. So you hit maybe at some point a fundamental problem if you think of science as an experimentally driven field, but that it really becomes very hard to do experiments to test this period of time in the universe. Okay. So you need some guidance, and that's where naturalness comes into the picture. And so this is just to say that this natural history then is based on this really amazingly small table of elementary particles that makes, as far as we know today, makes up all the stuff. Well, we know it's not fully complete, but at least up to very high energies and very short times after the Big Bang, a billionth of a second, we can describe the universe with just this small set of particles and the theory, which could also be written on the screen of a similar size. Okay, so we have some quarks, we have some leptons. It's not so important at this point. We have some force carriers, and then we have since 2012, and this will also be very important for this talk eventually, the Higgs boson, whose role it is to endow these particles with mass. So now let's pose this question. So is nature then natural? So I'll just start out by saying that the title of my talk is not trivial from the point of view of generically many fields of science, because many fields of science have different opinions about this. So here's one sort of course very broad statement by Mary Catherine Bateson that says that everything is natural, because if it weren't, it wouldn't be. So on the one hand, this is of course a statement that has actually quite profound implications for something like ethics, but it obviously doesn't have much predictive power if we want to use this as a guide towards testing the universe. And and this concept goes back further than Bateson to other people thinking about environmental ethics. So, but where of course this also has implications. So in environmental sciences, later on there has been let's say more sharp definitions of what you should think of naturalness. So not everybody is willing to agree with this, as you pretty well know. One attempt of making a more, so this is in the works of the author himself, a scientific concept for environmental science that can actually be evaluated and quantified. It's just given here as one example from environmental sciences. So, for example, the degree to which the system would change if humans were removed. So this is basically a concept of naturalness that says that everything humans do is generally unnatural, broadly speaking, and everything else is natural. It also enters in mathematics. So on the one hand, natural enters in very well-defined technical concepts like natural number, but it also enters in, you also see naturalness invoked as a judgment of a proof, for example, in a way that's maybe a little less precise. So you will see words like natural solution, natural explanation, natural argument, where maybe it becomes a little less simple to define what is actually meant by natural here. And these authors have actually studied the frequency or the rate of natural appearing in math papers published in the American Mathematical Society, I think it is, from the 40s to 2009. And you see that the rate is increasing steadily, so the call to nature is also pervading mathematics at this point. And you have similar concepts entering computer science and linguistics and so on. So of course, I'll be interested in naturalness in physics mostly for this talk, and the starting point for working with this is a kind of bleak outlook, you might say, but we'll soon make things look more bright, which was formulated by Philip Nelson back in the mid-80s. So he says, first of all, claims that theoretical physics isn't what it used to be, because what has changed from the old days is that now you have, this is exactly what we were talking about, legions of theories, so many theories that all give plausible explanations for the same phenomena. Okay. That in itself is fine. Then of course we want to test this with the experiment, but as is his claim at this point, in practice then, these theories now pertain to such high energies that it's hard to fully test them for two reasons. First of all, because it's becoming increasingly hard to compute anything in these theories, and it's becoming increasingly hard to do the experiments required to test these theories as we go to higher energies, shorter and shorter scales. Okay, so I'm just putting that statement up. And of course, predictions are hard to make, not least about the future, as somebody claimed. And today, we have the amazing situation that at least since 85, right, we've now constructed enormous experiments which were only beginning to be conceived of in 85, and such as the Large Hadron Collider at CERN, which is today the experiment where we are able to probe the smallest distances of physics. And of course, computational power has increased dramatically since the 85. So today we have supercomputers able to do, including here SU, able to do computations that maybe were dreamt of, but probably weren't thought of concretely at this point. Okay, so I would start. So the situation is not so bad. And just to set the stage, in the last 5 years, we had, at the smallest scales imaginable, we had the discovery of the Higgs particle that many of you probably have heard, and this will play an important role in our talk, in 2012, in July, at CERN. So this is now probing scales of the order of 10 to the minus 18 meters. And in the other end, on very large scales, we had the LIGO experiment this year detecting gravitational waves explicitly for the first time, which gives us hope that this might become a completely new experimental technique in astronomy. So we might have what you might call gravitational wave astronomy. If you think back to my picture of the universe, so the smallest scales we test in the lab, but the largest scales, besides being connected to the physics of the small scales, we study that directly, right, in astronomy. But all astronomy essentially is based on observing light, so light waves, right? So the light coming to us from distant objects, and we infer something about the large-scale structures of the universe. So having observed gravitational waves, without having to go into details, essentially offer you an entire new astronomy in principle. And I also show you this because it's a good example of how, this is important I think today to stress with the current political climate, how basic research really drives technological advances, right? Because these experiments were not technologically possible when Nelson was making these statements. It's really the conceiving of these physics problems that you want to experimentally test that has driven technology to the point where we're actually able to do it. Okay. Nevertheless, it is true that the timescale of building an experiment like the Atlas, the LHC experiment at CERN, this is the one of the detectors there, Atlas. There's a man here, so you see the scale is a multi-story building. It's 30 years. Something like 30 years to build such an experiment. So it is true that it is becoming very hard. Very hard. So, as a theorist, that's a window of opportunity, because the converse of that is that it becomes increasingly important as for theorists to narrow down the types of models that you want to test with these experiments. So there's something, the point underlying that is that you cannot, a given experiment will not be able to test any possible theory. Okay? So, therefore it becomes more and more important to think about what are good theories from a theoretical point of view while waiting for data. And in other words, so naturalness in a sense is just another word for a good theory. And this is just to illustrate the issue which has come about in modern physics, namely that today we are able to probe scales. So this is GeV is a giga electron volt. It's just an energy scale. It doesn't matter so much what it is. But this is the largest energy scale that we are able to probe today experimentally at CERN. Okay? So this is the energy scale that we currently are testing the standard model of particle physics at. But from the physical constants of nature alone, such as the speed of light, c here, and the gravitational constant, and Planck's constant, we can construct a scale which is 16 orders of magnitude larger than this scale. So there is, at least before thinking further, there's physics, potential new physics going on at a scale 16 orders of magnitude larger, which may or may not affect physics at this scale. And how do we possibly test such physics, right? 16 orders of magnitude is a huge, huge number. If you think about the experiment before LHC, it basically was operating at 10 times smaller, at a 10 times smaller energy, so it took 30 years to get to a factor of 10 energy. Right? So this, at least naively, poses really a huge challenge for us. Right. And this is just to show you that those energy scales really become very concretely relevant because we have a standard model of cosmology that tells us that the universe was very, very energetic and very dense in the early times after the Big Bang. And so those energy scales also, in the evolution of time, were important. Okay, and this is just phrasing the gap between these scales in another way. So these scales are also related to the strength of interactions. So the interactions between particles, like the electromagnetic interaction or the gravitational interaction. And if you construct the strength of interactions in a dimensionless way, you can get a number which corresponds to, so you get a number which is 1 with 33 zeros after it, okay, which is the difference, if you wish, in strength between gravity, which indeed becomes strong at this scale, and the weak force, which is the force relevant for Higgs physics going on at this scale, electricity. So there are forces in nature with an enormous discrepancy in strength, right? So there are these huge, huge numbers. So of course that immediately also poses the question, why do you have such huge numbers in physics? Just from naive physics. Okay. So I won't. So I think I can come back to this. Okay. So now. Well, maybe I should mention it. So how do you get funding agencies then to build you a collider experiment like the LHC, the biggest we have so far, to test new physics? Well, in the case of the LHC, we could really make a solid theoretical prediction that the current standard model of particle physics will break down at this scale, at least in what we call the conservative sense. Okay, so this is a prediction you make from theory, just a solid computation. Okay, so at this energy scale, the current model we have, there are some features of this model that mean it will no longer be a valid model at these energy scales. Processes start to happen too frequently, and you start violating probabilities, which is a fundamental concept of quantum mechanics that we built everything on. So something has to happen at this energy scale to restore this problem. That a possible something, so a possible new physics would be a Higgs boson. Okay. So when I'm saying it breaks down, it's without a Higgs boson. Up until 2012, we did not know about the existence of the Higgs boson experimentally. But we could say that if we build this machine, we will find the Higgs boson or some other new elementary particle physics that cures this problem. Or our whole foundation breaks down, which in a sense would be even more interesting. Okay, and indeed this happened. We found the Higgs boson. Okay, so now we found the Higgs boson, and there's no, okay, so let's leave it at this. So the question, well, okay, let me just rephrase that. We found a new particle that, to a large extent, with current data, looks like the Higgs boson. Okay. So now moving on. Yeah. So how do we move on from here? Ideally, we just build a new experiment, but that will take a long time. So we would like some theoretical guidance to, for example, what kind of experiment would you build, or while we wait for more data for LHC, some theoretical guidance of whether this particle really is the Higgs boson predicted by Peter Higgs back in the 60s, or it's something else that just at this point looks like the Higgs boson. Okay, So can naturalness help us with this? So let's discuss now naturalness in physics. So we would like, also in physics, just like in environmental science, a naturalness concept that can be evaluated and quantified. And of course we would like it, if we want to actually use it to say something plausible of future theories, we would like it to have proven predictive. And as you will see, such a criterion actually exists in physics. So before going on with this discussion, I just want you to keep in mind that there is actually different versions of naturalness that we can think about. So for the purpose of this talk, I'll call it structural naturalness, so that actually goes back to this again. Structural naturalness, numerical naturalness. So for particle physicists, I think we more often refer to this as technical naturalness. And what we call strong naturalness. So already here we see that the naturalness of nature is not a priori so trivial. So what will we mean by this to get some quantifiable concept? Okay, so let's first think about structural naturalness. So this is perhaps the least precise concept, and it's something which is nevertheless all the time used. So this is also why I go on about this. These are really practical tools. So this is very akin to something like simplicity or beauty of your of the theory you're trying to construct. So an example would be to compare the Ptolemaic model of the solar system. So here just one planet around the Earth, to the Copernican model. So here it's all the planets. So maybe graphically it's a bad comparison, of course. But the problem that Ptolemy faced was that you observe retrograde motion of the planets if you look out on the planets, which means you observe the planets that they appear to be shifting the direction that they pass us. Okay, so the direction with which the planets pass us appear to be shifting. So you wouldn't have that if, like people preferred at this time, the Earth was just sitting still and the planets were moving in nice circles around the Earth. The planet would always pass you in the same direction, east to west. So to incorporate that in the model of the planets, you had to introduce epicycles. So basically, you wanted to stay with the circle because the circle was the perfect theoretical object. So the natural mathematical object, if you wish. So you had to put epicycles on top of the circle. So epicycles on top of cycles. Okay. So what Copernicus did was instead to postulate that it's actually the sun that's at the center, and then the planets go in circles, or rather ellipses, around the sun, and then observations emerge. Okay. So you might think that especially if I now showed all the planets and all the circles and the cycles and the epicycles, right, you get a very complicated picture, at least from our point of view today. But it's sort of really ultimately, so you might say this is a structurally unnatural model. This is a more natural model, a simpler, more beautiful model. Okay. But that actually maybe really depends on your point of view. It's not so simple to quantify, and in fact already the Greeks, they had another structural naturalness argument that this model couldn't be right. So the argument actually was, so it's an interesting argument, the Greeks knew sort of how far the furthest planet was away from the sun and away from the Earth. And then one natural argument from them was that, well, then the stars that we also see are not that much further away. Because it would be unnatural structurally to have a vast distance out to the star from the furthest planet. But then, if the stars were sitting out there, then this effect that is called parallax, so the fact that as you observe an object with respect to some fixed stars further away, the object will appear to sit differently with respect to these fixed stars depending on your position. If you've moved, observed from a different planet to the Earth, well, this parallax effect will be big if those stars are close, okay? Which they were in the Greeks view. Why would they be far away? But they were actually able to measure that there was not such a parallax effect as you would predict from this. Okay. So this couldn't be the picture. And the underlying assumption was that it was natural for the stars not to be far away. But today we know the stars are vastly further away than any distance in the solar system. Okay. And we have let's say in astrophysics, then we have a new natural length of that. So this is just to say that this kind of naturalness, what's actual natural, is not maybe so easy to quantify. Yeah. So the other concept of numerical naturalness is maybe easier to quantify. So the first version you might think of is just to say, well, again, this is a bit intuitive, but doesn't, oh, sorry for this, but isn't it a bit strange that the Earth should just be sitting still? Which it did in the Ptolemaic view, right? I mean, a velocity of 0 seems a very special number. Right? It's a very special number on the set of all numbers. On the other hand, maybe you could say that for kind of n. So in principle, this is a predictive naturalness criterion, right? This model really ought not be right because velocity 0 is just too special. Of course, any kind of number you could think of is too special, so you maybe need to sharpen this a little bit, and you can do that because what you could do at that time is that you could in principle observe that this is just to illustrate. In fact, all the planets more or less have the same velocity, which happens to be of the order of 10 kilometers per second. Okay? So if all the planets you see have a velocity of the order of 10 kilometers per second, then it really is very special if the Earth would have 0 velocity. So that's numerically unnatural. Of course, that doesn't absolutely prove that it's wrong, right? But okay, so this brings us now to the. So this now sharpens this point that the concept we're looking for is something like numerical naturalness, something along these lines, okay, that can be evaluated and quantified and is proved. Okay, it can be used for predicting what future theories are good and what aren't good, even in the absence of data yet, ideally. So what enters into establishing this? Well, so it's relevant to think about some other concepts that we today have come to think of as first of all being documented by the evolution of physics and what good theory should be about. So in physics or in natural science, so it's typically reductive and it involves hierarchies and the concept that you could call fundamentalness, which again is very similar to hierarchies. And hierarchies here, I think, in hierarchies in length scales, for example, or in energy scales. And then very crucially, in modern times, so this century, symmetries. This last thing we can skip maybe. So the reductivism is, of course, that you would like your theory to go from kind of a complicated description to a simpler description. That again is not so precise, but here's an illustration of how things have worked in particle physics. So we started out realizing that matter was made out of molecules sitting in some grid, and then as time went on, experiments got better. People realized that actually these molecules are made out of a nucleus, and then electrons around this nucleus. Then it was realized that this nucleus, so we're going towards smaller and smaller scales, and simpler things, in a sense at least, simpler constituents, okay, that make up all these structures that you could construct with molecules. Then the nucleus turned out to be made out of protons and neutrons, and then they turned out to be made out of what we today call quarks, so all protons and neutrons, and all nuclei can then be made from just a few quarks. Okay, and this process has to do with scale, right? So as this process happens, you go to smaller and smaller scales. Actually, in cosmology, it's a little bit, it's the opposite. The world becomes simpler and simpler on larger and larger scales. So cosmology, the standard cosmological model assumes that the universe is homogeneous and isotropic. So it's the same in all directions and on all distance scales. Which is obviously not true on small scales, right? It's complicated on small scales. There's some structure there and there's nothing there, and so on. But on large scales, this smooths out. So it's not given that it will always be like this, but this is how it is in particle physics. Okay. So, and fundamentalist also goes along with what is called the principle of insulation. Again, in particle physics, we would now call this renormalization, but a more general term used is insulation and incomplete theory. So today, we have this picture that a theory describing the atoms, so the atomic theory, just because we realize that the nucleus is made out of protons and neutrons, some small constituent, it doesn't mean that this is a bad theory. It's just that the validity of domain of this theory, it only pertains to the length scales, to certain length scales, okay? There are only certain length scales where this is a relevant description. If you go to smaller length scales, it breaks down and you have to use another theory, a more fundamental theory, which however should reduce to this theory as you go back in length scales working in this theory. Okay? And that's a very fundamental principle actually. And the higher scales, so for that to work, the higher scales, and when I say higher, it's now an image in length, it would be the smaller scales. For this to work, they have to be separated from the other one. Okay, there has to be a separation. Because otherwise it wouldn't work. So the details of the more fundamental theory, the one at higher energy or equivalent to smaller scale, can only enter in a very specific way in your previous theory for this picture to work. In particular, it can enter into the specific values of your previous theory. So a concrete example. In fluid dynamics, there's no explanation of densities and viscosities of the objects that you study, the macroscopic objects that you study, and typical viscosities, typical densities of stuff is sort of the same same magnitude. Where are these numbers coming from? They're parameters. They're just input to the theory of fluid dynamics. But as you learn, as you went down in scale, you realize that behind fluids there are molecules, and it's the physics of molecules, it's the kinetic physics of molecules that determine these effective parameters. Okay, and the details of your kinetic theory will any varying kinetic theories will give different values for these densities and viscosities once you go back up to higher scales in fluid dynamics. Okay. And then you can find the correct one. Good. Okay. So the final concept, which is crucial as we go into the particle physics regime, is symmetries. Okay. So if we go back to our Copernican solar system, then why is it ultimately that the planets move around the sun in the way they do? Well, this is governed by Newton's laws of motion, which says that the force, which is a vector, it's the magnitude of a force and it's also a direction, is proportional to is equal to the mass of an object and the acceleration. So the force of an object is equal to the mass and the acceleration of the object. And even though this is an innocuous looking formula, there is a lot of deep structure here. And the first thing to notice is that the acceleration is the change in velocities. Okay, so you have difference of two velocity vectors. Such a difference doesn't change if you shift the coordinate system that you look at it from. Okay, so there's a translational symmetry. You can shift your coordinate system arbitrarily, and you'll still observe the same physical values. Provided this mass parameter is a constant of space. Okay, so provided the mass of a particle doesn't depend on whether I'm here or there. So there is such a symmetry in this law. And now if you go the other way around, if you're now a theorist constructing a theory, if you now impose translational symmetry on your theory of gravity, well, then you impose a constant mass. And you also impose a very fundamental property, namely momentum conservation, alone from translational symmetry. So symmetries restrict the possible equations you can use to describe a phenomenon. Okay, dramatically. And okay, so this is a special law of the Newton's law of gravity that only holds close to the surface of the Earth, right? So I really should have put the correct one, but things were shorter. Press for time. So there's another interesting thing, that the mass here in Newton's second law and the mass here in the gravitational law, the law of the gravitational force, so the inertial and gravity mass, appear identically experimentally. This is an example of something very unnatural. Why would this parameter, which tells you about the inertia of an object against being moved, why would that be exactly the same parameter as the one that tells you how much does it feel the gravitational force? But they are, experimentally we observe them to be the same. So this is let's say this is an unnatural coincidence. They could a priori be anything. But this is also explained by symmetries once you go to general relativity. Okay, so now let's come really to particle physics in the central part. So in particle physics, there has been, in the history of particle physics, there has been a range of numbers which and still are, which are vastly different and really begs explanation. Okay. And unnatural occurrences of unnatural numbers. So one example is what led to the concept of the nucleon. So what people realized once they knew about protons and neutrons, they realized that these protons and neutrons felt the strong force, so one of the four fundamental forces in nature, identically. Okay. So why would the strong force act with identical strength on a proton and on a neutron if these are two different particles? There's no reason, but what one realizes is that if you impose a symmetry which essentially exchanges a proton to a neutron, so that from the point of view of this strong force, they are one and the same. They're two realizations of the same underlying particle, the nucleon. Then this coincidence is immediately explained by its structure. Okay, so what I'm trying to argue, I don't know if I'm making it clear, is that you're reducing a naturalness problem to, you're giving it a structural explanation. Okay, so if there's a symmetry behind, you understand it. So there are much more extreme numbers, differences of numbers in the standard world of particle physics. For example, the photon, well, our theory today tells us it's actually massless, but experimentally at least we know that it's enormously much smaller than the electron, to the point of something like 1 in 10 to the 20. Okay. So how can that be? Why would there be such a vast difference in mass between two particles in this small set of particles entering the well, today we know that there's a symmetry, okay, which is not there if the photon is massive. It's only there if the photon is massless. So if we take this symmetry as a fundamental principle of nature, a consequence is that the photon is massless, and then this ratio is all of a sudden explained. Okay, so it's explained by this concept of symmetry. Why is the electron mass so much? Then you can say, well, then why is the electron mass so much smaller than the Planck mass? So what is the Planck mass? That's basically just this energy scale, the highest energy scale we could construct from these fundamental constants, this 10 to the 19 GeV I talked about. Well, again, we realize that there's a symmetry which can protect the mass of the electron, ensure that the electron mass is very small, and here there's a slight detail that I'll get to in a second. But essentially it's the same story. In this case it's called chiral symmetry. Okay. And finally, a slightly more mundane example maybe, but the consequences aren't, is the difference between the pion mass and the proton mass. So the pion is a particle made out of 2 quarks, and the proton is made out of 3 quarks. Quarks weigh almost nothing relative to the actual masses of these particles, so there should be no difference between having 2 and 3 quarks. Nevertheless, the pion is an order of magnitude lighter than the proton. Why is that? Again, we find that there's a symmetry that can explain that. Okay? So there's a symmetry which, if you dial these two masses in your theory to be the same, this symmetry was no longer present. Okay? So if you take the symmetry as a principle, then this is a consequence. Okay? Of course, the symmetry. So now we come to sort of the crew of the matter I'm trying to get to. Now, if we take so if we now go back to this story of insulation and symmetry, so the point that we had was that for this whole chain of events which has worked in physics to work, it means that if you're studying physics at some scale, then even though something else is going on at a higher scale, energy scale, or smaller distance scale, so even though the nucleons aren't particles at all, they're actually just fundamental. They're made out of quarks, let's say, something completely different. Those details can't matter at the energy scale you're studying. Okay? Because otherwise, your theory couldn't work. So we need this principle of insulation. But now we get to an interesting problem, namely that so we talked about hydrodynamics versus the underlying kinetic theory. In particle physics, the details of any high scale, all your particles, whatever they are, they do feel what is going on at high energies because of what is called quantum effects. So in fundamental particle physics, there is no such thing as a vacuum, which is just void, a complete, total, classical void. there are always particles popping in and out of the vacuum. Okay, so any physical particle feels, for very short time scales, in a way I think, feels the physics going on at high scales. Okay, a priori. So how can this insulation work? Well, it can only work. So that's why it can only work if you have such symmetries, because otherwise, something like particle masses, for example, will always be sensitive to the highest scale that you have in your theory. It could be the Planck scale. So it's unnatural for any particle mass without a symmetry, a priori in particle physics, to be light with respect to the Planck scale. Okay? And nevertheless, we observe all the particles we observe are very light. So we understand that today if there's a symmetry protecting them. Okay? So that's sort of the upshot. If you have a symmetry, we can have particles that are light with respect to this scale, which is another way of saying the physics going on down here, where you also have the particle masses sitting, is insulated from these very high scales. Now, if you look at the standard model of particle physics before 2012, that was all well because all the particles came with the symmetry doing just this. Okay. However, the Higgs boson, which we discovered in 2012, doesn't come associated with any such symmetry. Okay? If by the Higgs boson you mean the theory that Peter Higgs wrote down with one fundamental new particle, which differs from all these by what is called its spin. It's not really important, but it's different with respect. It doesn't come with such symmetries. Okay. And we actually know, so we have a problem. So how can we find a particle with a mass down here, this energy scale, when there should be physics going on at least far up here towards the Planck scale, when there's no symmetry? So now we are faced today with an unnatural number. Okay? So the mass of the Higgs particle is unnaturally small. Okay? So now naturalness enters in, you might say, as a prediction. Of course, it's not really a true prediction, but it tells you that the standard theory, Peter Higgs's model of the Higgs boson and these mechanisms, is unnatural. So can it really be true, despite experiment? So far, it's confirming it. And we actually have historical examples. So this is concretely to show you. There's a notation on this. This lambda here is supposed to denote an energy scale. Okay. So previously in history, we've discovered particles just like the Higgs boson, which for physicists means particles with the same spin as the Higgs boson. That doesn't matter. Okay. So particles that walk and talk like the Higgs boson, which were found to be very light. So at the scale of nucleons, for example, this is the pion I was talking about before. The pion is very light. Okay, it's the same mass as the proton and the neutron, but it's a scalar particle like the Higgs, so it should feel all the physics going on up until the highest scales existing, and therefore its mass should be sitting up here. It should be a mass which is vastly bigger than what we actually observe. Okay. And this basically shows, and also, for example, the difference between two different pions, which is observed to be tiny, should be huge if this scale, energy scale here, which could be, for example, Planck scale, is huge. Okay. So these masses are far. This difference is far below a GeV, but it's proportional to something that a priori could be 10 to the 19 GeV squared. So this is completely unnatural, and as it turns out, indeed, these particles aren't fundamental. They prove to be composite, made out of quarks. And the quarks themselves do have a symmetry. So then you understand structurally, this naturalness problem disappears. Okay? This computation is false because they have structure. And this has repeated itself many times. Today we're faced with the same problem for the Higgs boson, if it's just a fundamental particle, as data so far is consistent with. Okay? It's not conclusive, but it's consistent. Again, you have a similar formula where the Higgs particle mass, and again I apologize I didn't put a lambda here so it became clear, but the Higgs boson mass is proportional to we call it the cutoff of the theory, the highest relevant energy scale in the theory, which again could in principle be the Planck scale. Could be. Okay. And there's a number in front, but this number is not zero, so this naively is a huge number. So again, why do you find it to be a mass here at this scale when there are effects that would want to pull it up to much higher energy scales. So just to give you an analogy, this is similar to if you think about, let's say in statistical physics, if you just have a gas of energetic particles, okay, and you take a particle at rest, so which is okay, so think of its kinetic energy as the equivalent of its mass for now, okay, and you dump it into this bath of very energetic particles. Well, after a short time, all these very energetic particles will have bumped this particle at rest and kicked it and kicked it and kicked it, and it will have, after a short while, it will on average have the same speed as all the other particles and thus the same energy as all the other particles. So it was unnatural for it to have a low velocity in the system, and indeed the other particles will kick its velocity up to this scale. In quantum physics, it's the same thing going on. This kicking endows the particle with an actual mass in the atoms of symmetries. So although the Higgs, as I mentioned briefly, solves this problem of unitarizing W scattering, which was so in other words, it cures this problem that the standard model breaks down at the 1 TeV energy, which was basically the reason why you could get money for the LHC experiment in the first place. And although experiments seem so far as consistent with this being a Higgs that does this, this would be an unnatural, solution. Okay? It's unnatural that it's the Higgs that solves this. Okay. So, in the interest of time, let me skip this, and just to say, repeat a few points. So there is an interesting, comparison here. The details don't matter. But if you think about the sector of the standard model explaining, for example, the electron that I mentioned before. So the electron is very light with respect to the Planck scale, or with respect to some other scale. So before discussing symmetries, that would be unnatural. Okay. But we now know, due to symmetries, why the electron is so light with respect to this. It's insulated. On the other hand, if you look now at this sector of the standard model that we today are probing at the LHC, let's call it the Higgs sector, the physics of the electroweak scale, actually, if you look at it, the mass of the Higgs, so this is a bit misleading compared to what I said before, but the mass of the Higgs and all other parameters are sort of the same in this sector, are all of the same size. Let's just say it like that. So that would be natural, naively, but once you think about quantum effects, this one up here becomes natural, but this one down here becomes unnatural, and the theory is a quantum theory, okay? Because the Higgs should get quantum effects pulling its mass up. Okay. So, what are the explanations of this? And then I'm done in 1 minute. When were we supposed to end?
Yeah, a couple of minutes.
Yeah, okay, fine. So what are the possible explanations? Well, this is essentially the formula that's the problem, right? So you have some Higgs mass that you would like it, the observed one, but naively these quantum effects of this size wants to push it up to some very high scale. Okay, so you have three naive solutions. You just postulate, well, the Higgs doesn't exist, so people have studied such models, something else unitarizes the theory, and that was a good explanation up until 2012, when we really found a particle that walks and talks like the Higgs. So such models don't exist anymore. Then there are, in a sense, two other solutions. Either you have a symmetry which makes this prefactor very, very small. Okay, that would be unnatural without a symmetry. It's not natural for this prefactor to be very small because it's a combination of many parameters. Yeah, here we go. Okay. That dopes them up to 0 in a natural way. But if there's a symmetry, that could be, so something called supersymmetry is a theory, is a new theory with more particles, okay, that have not yet been confirmed, have not yet been shown to exist, but the theory does this, okay, it ensures that this parameter is time. That's one way of thinking of it. Equally, actually, you can say that the scale is time. Never mind. And composite dynamics is another one, like for the pion, if you assume that this particle is composite, suppose the Higgs, it isn't actually fundamental, it's composite, then it's the same situation as the pion. Then there will be chiral symmetries that ensures this. That's very small. So your theoretical bias might now be that it isn't Peter Higgs's model as the correct one. It really is supersymmetry and composite dynamics, and then we have to think about how do we actually test these theories. Of course, we are trying to test them at LHC already. So this is just to sort of show you, so long story, cut a long story short, how naturalness considerations lead you to, at least on naturalness grounds, reject one theory which does fit with experimental observation so far, in favor of other theories which, if constructed at least appropriately, also explain current data, but will lead to additional future predictions that can then be tested. Okay? But this testing is a very complicated process, so naturalness is very useful. Okay. Of course, naturalness might not be the right principle. Okay, so there are alternatives to naturalness. One is anthropics, which is driven by the observation that all the parameters of our current standard model, if you change them a little bit, it appears that it's very hard to produce life. Okay? So you might say that all the parameters of the standard model are the values they are, even if they are unnatural in this concept. Because otherwise we wouldn't be here to observe them, because life wouldn't exist. And other explanations along the same line, but with some different implications. For example, if the theory, the underlying theory, is extremely complex, you can have accidental, you can have things that are accidentally very different. Or you can have something like a critical phenomenon. Maybe it's a critical phenomenon that the parameters of the standard model are what they are. Okay, so I won't go further into the details. I think I'll actually stop at this point. That today we're then trying to construct models of composite dynamics and supersymmetry motivated by naturalness, and studying how do we then test them, ideally with current experiments, or what future experiments do we need to test these and distinguish between. Okay, thank you very much.
All right. So now let's get to the business. So let's grill him a little bit. So it's any questions before I start giving you?
So what scales do you predict to, what kind of colliders do you need to test these current theories if we take the composite or the supersymmetry?
Yeah,
How much funding do you need?
Yeah, that's a very good question. So it's hard to be very precise, okay, because it depends, because this comes back to this computational problem. So if we start with composite dynamics, so there are different types of composite theories, and you can classify them, among other things, by the scale with which you start seeing the compositeness. If that scale is the same scale as the Higgs mass, the electroweak scale, okay, which it is in a class of models, then you can say something pretty precise as the answer to the question. And the answer is energy scales which are very close to where LHC is operating. So either at LHC, or if you're very unlucky, something just beyond LHC. But then typically you should begin to see something in tails of distribution. Okay, we haven't talked about that, but you should start seeing indirect hints in your data, even if you don't see something glaring. You don't see a new particle, you see some traces of a new particle.
So we can do that with existing equipment?
Yes, we can do that. So that's one class of composite dynamics model. Now, there are other classes. If now this scale of compositeness, which can be higher, okay, you have to just that scale also sits in the typical mass scale of new particles, and then it can be above LHC. So how far above LHC? In principle, arbitrarily high above the scale we now. At the expense that, and you might even have guessed this already, that even though you postulate composite dynamics to as a natural solution, if you now drive up the scale, what effectively happens is that you get a new naturalness problem, a fine-tuning problem between now the size of the scale and the scale of the electric symmetry. That sort of comes back at you. So there is a possible solution. It could be composite dynamics, and it could be arbitrarily close to the standard model at the energies we're probing now, and even at higher energies. Okay, so very hard to distinguish, but at the price of naturalness. But of course, you wouldn't, strictly speaking, know it. And with supersymmetry, something similar actually it's fully analogous. You can, within supersymmetric models, there is a naturalness classification, if you want, or a fine-tuning classification. And it's the fact that some of those models are natural. And those are the ones that you will be able to test at LHC or maybe with an experiment that's a bit better. So really, let's say rule out maybe.
So the argument to keep funding is we need to rule out these classes of theory we're trying to portfolio. It's
Yeah, but
just
that's
around the corner. Fund us
Yeah.
a few years.
Yeah. But that's a more
it's
tricky
not-
argument, right? Than yeah.
But it's not just one number. I mean, it will be too cheap if that's the case.
Sure,
Okay,
sure.
so throw it, we can live with a number and we can move on. But we still don't know what dark matter is. And any extension of the standard model that mingle with a number dramatically changes everything. So you still have to explain why all the masses, and one thing the message didn't say is that that particular little piece of information dramatically affects everything it makes us. So try to make a theory that works as well and solve the problem. That is a challenge. Right?
Yeah. So if you so that here I focused on this mechanism of, maybe I wasn't even precise, but the physics related to the Higgs boson is the generation of mass for the standard model particle. But actually, that there's more. So for example, you have here the neutrinos. You've now observed that the neutrinos are massive, but you cannot explain that within the standard model, and with the ordinary Higgs. Okay. So you know. So there are other. There's other physics in this model that tells you. I mean, there's other physics in the world that tells you this model is incomplete. Another point is the dark matter. Okay. We know most of the stuff in the universe is actually dark matter, and not, by all accounts, not made up by any of these particles. So those things, of course, you also have to search for. But that's at least partly a different story. And you don't. Yeah. Okay.
I mean, I think Matt has chosen to focus on naturalness.
Yes.
We can argue against or pro that particular way of actually using to go
Yes.
beyond. But it is a fact
Yeah.
that you have to go beyond.
Yes.
It is a fact
We know the
that
model
this
is
is not
incomplete.
complete. It is a fact
Yes.
that you have to make experiments to explain the other 95% of the universe.
Yes.
So it's not just, it's
Yeah.
that argument is a way to select some
Yes.
tiers out of the number of tiers you can explore.
But-
It is a fact that,
Yeah.
that any extension you make, depending on your taste about naturalness, has an immense number of predictions. Right? I can actually now construct a theory, fundamental theory, but fundamental means perhaps not as natural, but completely fundamental, as fundamental as the standard model, and where the Higgs composite again mass to all the standard model particles. That would predict 100 of states to be seen in the next 10, 15 years. The standard model doesn't predict anything else. That's pretty cool. So you can do shit
So
that changes stuff dramatically, and you can still actually completely ignorant about it. That, stressful. So.
there's actually a very interesting point is related to you, and since Francesco brought up dark matter, so just to re-emphasize that another information we have is that most of the mass of the universe is what we call dark matter. It doesn't shine light, and it then by a train of analysis implies that it cannot be made out of any of these particles, and has to have a little qualification, but most likely cannot. Okay, so it shows there are new elementary particles beyond this in the theory. Okay, now when you give your popular presentations, popular science presentations about dark matter, of course, what you focus is on that we spend all this time learning about 5% of the universe, and then there's dark energy. There's even more. Let's forget about that. But there's 5 times as much dark matter, right? So this is just a corner. This is just 5%. But if you're actually more honest, let's say in context of this talk, well, 5 times as much, that's 1 versus 5. That's natural. Essentially, it's the same amount as ordinary matter. Huh? So this is kind of an example of a numerical naturalness. Okay, so then you say, okay, so that's fine. Then there's no issue. But there is an issue, namely that the typical theories, not the typical, but for example, if you look at these classes of theories that were proposed to naturalize liquid symmetry, then the type of dark matter, okay, so it's an amazing fact that you can get dark matter from these theories also. They typically predict dark matter. And there are mechanisms to explain where you can get exactly 5 times as much. But some of these mechanisms, okay, and they are not unique to specific theories, but for example, in supersymmetry, the typical mechanism you use for getting the dark matter in the early universe is completely different from the one that gives you the ordinary matter, which is called very. So now, even though you have a natural number, and you have a theory that was meant to naturalize the Higgs mass, all of a sudden, this natural number becomes strange because two completely different mechanisms somehow conspire to produce the same number after the entire evolution of the universe. Two completely different origins conspire to give you the same amount of stuff in the dark sector and the ordinary sector. So that becomes kind of a
Yeah, so this pushes you,
different type of method.
this pushes you, not to be lazy. You cannot be lazy as an experimentalist. You cannot think that you can go by brute force constantly, right? That's typically done. People goes by keep doing what they're good at, not to think differently. That's typical in theory, typical in experiment, typical everywhere. So now that you know that there are alternatives, which are equally good, if not better than the standard model, test them. You cannot just tell me that I need to wait 50 years to do that, because there can be precision experiments with cold atoms, there can be precision experiments about transition on the atom. They are sensitive, they could be, and it might be sensitive to actually the physics. Electric dipole moment of the neutron is very famous experiment for that. So you have actually a portfolio of all the ideas that you need to actually think very hard. If you get atomic clocks, which are very, very good, why can't we use those? So we ultimately want to face fundamental problems in nature. We want to solve that because when we control them, we can make better things. When we understood how the positrons were invented, and I can do PET scanning. Once you understand, you can make things that you cannot dream of today. You can do now hadron therapy. So there's things you can do that came out of actually pushing the boundaries. So this pushes the boundary of human frontier. The more deeper you go, the better methods you can make. And there is a tendency to sit on our ideas. For example, LHC was conceived 30 years ago as a visionary thing. There was a competing program in US which was called SSC, superconducting supercollider, that was killed by political reasons. The ground was already in '96, the tunnel in Texas was already made, and because the other states close by didn't like that the jobs were going to Texas, was killed in Congress. That's the insanity of human beings. It was good for Europe because then Europe was actually able to construct a collider which was much lower in energy than was supposed to be the American one.
But this is at the heart of my question.
Yeah.
In order to keep this moving, you need close by goals that you can set out to
and do you
achieve.
do? I mean, so the question, yeah. So it works. I mean,
otherwise people might give up.
Yeah. But it works this way. I mean, theories construct theories that can be tested using paradigms that serve the purpose to guide you. They might be wrong. Nobody told you they're right. But they push constantly the ping pong with the experimental community to go and test it. You can be damn sure that the experiments are doing up for dark matter and might not be covering the right dark matter region, but it's the one which some of the models covers. So, but by even eliminating that possibility, those won't be the things, and a lot of technology being developed currently to be able to have this stuff. So, once you are at the boundary of human knowledge, you cannot guarantee something, but you can certainly guarantee that you're going to work hard and you can make new stuff. And naturalness is one of the guidance. I can actually at least present another 20 equally good guidances. Also pushing the boundary of theory per se.
But this is indeed the point that naturalness is a guidance for this region, for how you should go on this region. But I also want to just very briefly what Francesco said, that there are other in principle. So we don't have direct, as in a collider, produce this. We can't produce this energy scale, but there are actually indirect. Francesco also commented with access to energy scales of this order, or for example, looking for proton decay. So limits on the lifetime of the proton. So there's no fundamental reason why the proton should be stable. We observe it to be very nearly stable. So if you have a huge ensemble of protons and you wait, so you can't wait for the life of the universe, but if you have enough protons, you can statistically infer that the scale of decay of the proton has to be, or the energy has to be higher than the energy corresponding to it.
In the standard model, the proton decays. It's not a stable matter. it decays with a very, very slow rate, but
Well,
it decays. It's not a stable
Yeah.
object. So what is concerned is the difference between the baryon number and the lepton number. So it's the quantum number of the baryon minus the quantum number of the lepton, or the electron if you want. That actually is stable, but each of them are not stable. They will actually be mediated the decay, but with lifetimes, which fortunately for us allows our life to exist. Right. There are beautiful things happening, right? That actually.
So another line of thought is to try to think about, that's how those type of indirect experiments, right, that's going on, that can actually probe much higher energies, but in a less direct way, but still. Yeah.
I have a fairly naive question about naturalness as a guide.
Yeah.
So I was struggling to see, okay, can I fix it in my mind, or is it arbitrary? And it tipped my understanding so far that it is ultimately an arbitrary criterion. Is that true?
No.
Or do you see it differently?
No,
You can define
it's not arbitrary because it's
Fine.
because it's related to symmetry, so it's related to an underlying mathematical construct. But it's not. It's also not carved in stone. I mean, it can be a wrong principle.
There are two,
But-
okay, but two things. One is the use of naturality for making new theories, and that is not carved in stone. One is the mathematical definition of the
Right.
naturality. But you can mathematically define naturality using when you write your quantum field theory, you can define operators which are either supernormalizable or marginally irrelevant. These operators have their degree of naturality. So that can be mathematically defined. So you can construct a theory, and the theory of the standard model, for example, the mass operator of the Higgs is in a natural operator because it's actually quantum corrected. So, other ways of saying that the mass square of the Higgs, when you renormalize it in the standard model, is the mass square you have in the Lagrangian, which is a parameter you put behind. So this is the physical mass. This is the parameter you put in the Lagrangian, so in your theory. This is a function of the new scale of which you calculate with respect to the scale that you can take the physical mass of the Higgs. And so this would be a technically natural operator, because if this were the case, because it begs the question why the mass of the Higgs is whatever it is, but once you put it to zero, it will not be generated. But in the standard model, this is proportional to this other quantity here, which is calculable, depends on the theory. Now, this is the matter of the issue, because it tells you that even if you do not have a mass at all in your theory, the mass will be generated. So it's not a good number. You need to tune it. You need to tune this term against this to give you the physical quantity. The mass of the electron, on the other hand, is only so-called multiplicatively renormalized. So the physical mass of the electron is just the mass of the electron you put in the theory times a number. So what makes this difference? Why the mass of the electron? So now the question to you, since you have heard the lecture, why the mass of the electron is only multiplicatively renormalized? That's because when you set the mass of the electron to zero, quantum electrodynamics acquires an enhanced symmetry, and that protects the mass of the electron against quantum correction. Now, a symmetry is what you're begging for when you want to construct objects which are protected. Makes sense? I'm not telling you why the mass of the electron is 0.5 MeV. From a theoretical physicist, I don't give a damn. This is just nature throwing some numbers at you. But from a theoretical point of view, it makes an immense difference when I think about symmetries, because it makes my theory highly predictive. Quantity is highly protected. This will allow me to select a subsection of theories and make some theories more fundamental than others. That will, at the end, what will make a theory fundamental, or natural in this case. Fundamentality requires other constraints that super select the number of theories you have. If you do a theory for social organizations, you would like to have certain parameters not to be randomly distributed, but protected by certain symmetries. Right? Otherwise, what's the point? You just throw darts at the things and you get the result. So that's different from even in statistical mechanics. That's used. This is intrinsically related to the renormalization group, which is used basically now in any construction of reality, where this statistical mechanics, where this graph theory where these quantum field theories, these are universal principles, but symmetries are at the heart of any problem. Naturality can be classified on the basis of symmetries.
So the short way, maybe of saying the mathematically precise way to what Francesco did was that if you have a parameter, if you make an observation of something in your theory and you find this to be small, unnaturally small compared to something else, then if there's a parameter of the theory in your theory, such that when you send this parameter to 0,
Yeah.
you gain an extra symmetry of the theory gains an extra symmetry. Then the smallness of this observed parameter is natural,
Yeah.
and otherwise it isn't. And more precisely, that's what we call this technical naturality. Yeah, I did not phrase that precisely. Actually, I should have done
That's the beauty of it. And then people make construction on that, which are called fine-tuning. Fine-tuning is how much you, given the scale of new physics, which could be the Planck or could be the electroweak, or the top scale, sorry, the temp scale. So how much you have to tune this number here with respect to this to get the physical quantity. This is nothing to do, it's to do with the fact this is an unprotected operator, it's an unprotected mass, so you have to tune something to get the right result. And that is the problem of fine-tuning, how much you want to fine-tune it. Right? If you're fine-tuning from the Planck scale, then it's a fine-tuning of 17 order of magnitude to a fine-tuning of an order of magnitude. If that matter were, for example, around the tab, then you reduce the fine-tuning from 17 order of magnitude to the tab scale, which is only 1 order of magnitude, because new physics will be actually around the corner. But that's fine-tuning. It's not technical natural. So you see how many things you can say and mathematically classify.
I have one little follow-up, because I was thinking, okay, fine, I got this. Now, when I said arbitrary, I had one more thing in mind. Suppose you had wrong equations.
Yeah.
To what extent is naturalness then helpful?
So the question is that
Suppose you add
Wrong equations.
well, I mean, you can
wrong. What do you mean by wrong? You mean
Suppose you have an alternative set.
yeah.
So the question is that your set of equations must reproduce the results you already have. So you're going to deform your theory and try to make it natural, or trying to improve on naturality or in fine-tuning. And then what you will have to do is to make sure that it doesn't screw up what you already have. So it's highly non-trivial to modify your theory in such a way that the rest still works.
And the last point or question is, I thought naturalness jointly with the number of constraints,
Yes.
not only naturalness
Of
alone.
course, yeah.
Okay, fine.
Yeah. So
I
that
got
runs
you.
jointly with the no, but unfortunately, it doesn't uniquely fix the extension of the,
Right.
but it fixes a
class of theories.
class of theories. Yeah. So you have to have new experiments to get new constraints, to trim down these.
And of course, you can treat sometimes naturalness for fundamentalities. The two things are not the same. And you can, but you can again classify, and you can write mathematical classification of all the theories and their operators. And this is actually what guides theoretical physicists to better constructions of, or more, if you want, consistent constructions of the world around us. But it is a fact, every time we discover a more fundamental theory, this theory could not only explain what God, predict something else, and explain something else. I mean, for example, I would hate that the theory I will construct, the only thing it does is fix this number. I would love that this theory also predict that one. Because this is another phenomenon that's very well studied in mathematics, is reduction of information. A theory is better if with the same theory you can explain two things, three things. So naturality on its own, it's nice, but okay, so on. But you could also say, well, if the same theory is simultaneously explained, I can also show that the theory of the Higgs could also explain, for example, inflation. So if your new theory of inflation, theory, as dark matter, explains inflation, things like that, by all means, bring it up. That's not easy to do. Does that make sense? More questions? If not, let's take again mess.